Before I start, I welcome everyone online as well as here. I actually had to make a conscious decision to make a marathon here with case studies and imagery. Believe it or not, 100+ slides. And I'm more of discussion guy. So after 26 hours travel yesterday, we'll see how this will look like. Anyhow, what we did in the past couple of years, actually, since Himawari came, we were like small kids, just jumping in front of the roller coaster, just waiting to get there. Soon it will happen, hopefully. The launch is scheduled end of this year for the FCI. So we prepared a lot of cases. We were looking at many different things, and this is just only a subset of what we were doing in the past years, showing maybe the benefits of the new generation of satellites over Europe. Okay. So I start with a picture of SEVIRI here, deliberately because this is where we start from. Now, I have the updated version of presentation uploaded, but it couldn't be fetched, so I changed this, amended a little bit here, adding Jochen Kerkman. He did a tremendous work on preparation for the FCI, and also Hama Hamidou in the audience. He contributed to one of the cases. And this is the MTG satellites here. And what I'm going to mention is first, what is new with the FCI when we transition to new channels, and the difference is only 4 channels. The new or novel RGBs that we've seen around the globe being used, and we cannot use with SEVIRI now. What is this going to be like, and how beneficial is that? And then I'm going to just show. Oh yeah, okay. I thought.
1 second.
Oh yeah.
We have a frozen.
Okay. Then I'm going to talk about the products that we we had a few ideas in the meantime, what could be the new RGBs, and especially thinking of the 0.9 channel, the water vapor absorption channel, low level, how this could be utilized. And yeah, what is with the oldies, the standard set of RGBs that we were using in the past years, that will benefit from the maybe better spatial resolution or temporal. Maybe Dan, or I can set the alarm, or you can raise hand 5 minutes.
Sure.
Or something.
Yeah.
Okay. How do we do it? Okay, so the fleet is basically, MTG fleet is 2 imaging satellites, 1 sounder. So this is lighting imager and FCI. On these 2, one is special rapid scan and one is normal full disk. And we'll concentrate mostly on the imagery today. So this is African fish eagle, and like our bird, MTG, it flies over the continent, probably with years or hundreds of years higher and higher, seeing better and better. So with the MSG to MTG, we're not really doing a revolution here, moving from 12 to 16 channels. Conceptually, we're kind of there. We're just getting a little bit of evolution there, and how this transfers to is better resolution, spatial, temporal, spectral, and radiometric. Just a quick look on the numbers. So we move from 3 kilometers, 1 in a high resolution visible, to 2 kilometers in infrared, 1 kilometer solar, at the best resolution 500 meters. Temporal from 15 to 10 minutes, or 5-minute rapid scan to 2.5. Spectral from 12 to 16 channels, and I didn't include the number, but definitely better performances. So these are the channels. In blue you get the ones that will have advanced resolution. So in the solar region, we'll have two channels at 500 meters, so 0.6 and 2.25 microphysical, and 3.9 and 10.5 will come at 1 kilometer resolution, and that's very exciting, I think. Especially we've seen, I mean, this is we had the snow applications. 1 kilometer infrared is something that you could really start thinking about utility during nighttime. And yeah, these are probably the top 4 RGBs we identified that are very much different from our standard suite of RGBs we are using already in Europe. So I'll just go over examples of that. Okay, starting true color RGB. We have 2 dust events here. One is pull from the cyclone warm conveyor belt in the west, dust from northern Africa, and this is dust from the Middle East, and it's basically thunderstorm driven push over the sea. So aerosols are seen in this example very well, even the thin dust over Western or Central Mediterranean in this case. But you see also sun glint could be maybe not for the trained eye, but for algorithm it could be just a tricking. Just by the way, in the top right corner you have the recipe of the RGB I'm talking about. So true color RGB over aerosols over the land. Normally the dust is the same color of the land, but then you have an issue there. But unless you animate, so I've collected 4 consecutive overpasses of the polar orbiters, so you kind of mimic what FCI will see over the Middle East here with the dust event. Well, works or not? It didn't move previously. We had some movement, but okay. Anyhow, when you move this in time, you start seeing your dust. So it's quite important to animate things. I'm sorry, I don't know why. I'm going to move now to this side a little bit. So this is another example. I hope this one moves. The same thing, 3 consecutive days of polar overpasses, and it kind of mimics what FCI will see in motion with the true color RGB. So this is Iran, Pakistan dust events. Then this is very interesting event from Europe. The first dust event, real dust event, originating from the Europe. The dust clouds originated from Poland, Germany, Sweden, Denmark, and you can see the dust plumes really extending from southeast to northwest. And also you have the plume of smoke here. What is interesting here that you have different dust colors. So depending on the source, you have more brownish, more pale dust here from Poland. That year the soil was very dry, so the strong wind event induced this dust lifting. Aside from having a dust being seen, we can identify different dust colors, and this is not possible with the dust RGB, of course. Neither true color RGB, natural color RGB that we're using often has less information here, obviously. And this is a very vivid example from Libya on the dust color difference from the true color RGB. Smoke, we've seen the smoke in Sweden previously. Now smoke from Greece extending over Mediterranean, and obvious example that if you go towards shorter wavelengths, you see better the smaller aerosol particles. This is what we have today, and this is what we will have with the FCI. Sea spray as well, strong bore events off coast of Croatia. So the very strong winds getting across the Mediterranean, producing sea spray, and you can see the streaks of these over the whole of North Adriatic. And the strongest points here with the rotors of these winds, the sea spray changes the ocean color, sea color. Speaking of ocean color, okay, I had the comment here, treated here with caution. We had exchange with the ocean experts, and they said, whoa, don't call it ocean color or whatever. And there is a very good reason for that. I'm not going to go into details. Anyhow, the ocean color people, they have much more bands in the visible spectrum, and they choose them accordingly, and they know more about these things. But anyhow, there is a bloom of different species in the ocean can be tracked. Not only that the visible recognition is important, but also the shapes and the colors. They tell much about what's happening. So if you see the shapes here over the Black Sea, you see that it kind of, you can track really the currents there. So this is consecutive overpasses of Olchi, which, by the way, is a true ocean color instrument, and you can say much more about this. So true color RGB, and maybe the last application. This was a passage of Batsirai, I think, cyclone over Mozambique, and floods in the Punguele River mouth around. You can see very muddy waters around. Probably you would better use, I don't know, radar instrument, but at hand you can, as a first guess, use true color RGB. Okay, cloud phase RGB. So we're looking into microphysics of the things. Starting with the previous example, we still see the aerosols, especially the thick dust. Thinner dust, we start losing the signal there because we're moving towards infrared more. And sun glint is still here. Thunderstorms in blue, whitish clouds to pink is a low level of water clouds. If we move to what we have today, this is natural color RGB. We're getting to shorter wavelengths and seeing actually a little bit better the dust event. And as a previous example, the best weapon of choice would be true color RGB in this case. Of course, the cloud phase RGB is here for the clouds. So I'm showing very colorful example, I think from Maria here. And this was a so-called DIBS event, so the dust infused a cloud system, which has small ice particles on top, hence in this more pale bluish shades, also very cumuliform cirrus clouds. So you have different shades of clouds with this RGB, and also the background changes colors. We're having some vegetation information in this RGB as well. I'm not going to go into details because I'm running here. Actually, cloud phase RGB for snow applications. Different shades of snow tell you about the different microphysics. But be it older snow or bigger grains, higher snow in higher altitudes, like in Alps, it's more pale because of the smaller crystals. And we'll concentrate here on the Iberian Peninsula now, where we had an extensive case study on this one. You can read here. By the way, down there you have all the links to the case studies, which I'm showing here, so you can read much more about the everything. Anyhow, the color changes depending on the grain size, actually the size of the snow. So this is how we find it useful in the winter season. In the summer season, this is obviously a thunderstorm. And what is interesting here to know, it's a little bit burned image. Sometimes we don't when we do these proxy cases, we take whatever we find, and then we do different tunings for different instruments, obviously. And this one was not very good one, but anyhow, what you can see here is transition of the phase from purple to blue, where you see the glaciation, where you're interested which part of these low clouds will start being dangerous ones, and you have some ripples on top, etc. So this is again Batsirai, I think, cyclone. And aside from what we have today, and this is convection or severe storm RGB, which tells you about the most intense parts of the bands around the tropical cyclone. This RGB doesn't tell you about the low-level clouds. It's concentrated on the high levels. So here you have much better situational awareness, where you still keep the information about the particle size on top of the clouds. This is a very nice example. I think also Maria worked on this one, where we saw industrial plumes over the stratus clouds. So stratus cloud moved. There was an anchor point source of small particles induced in the stratus, changing the microphysics and hence the microphysical signal here. So everything that is in more yellow shades is small ice particles, very nicely seen by the cloud phase RGB. What we have today is this day microphysics RGB, and we see that it actually outperforms the what we have today. Very encouraging. Okay, cloud type RGB. The basic idea is to have this 1.3 series band that can see only the highest clouds, and we start with the aerosols here again. The long band of smoke actually emanating from I think Canada in this case, well seen by this RGB across the Central Europe towards the east, confirmed also by Calypso. How hard is it to see that nowadays? Even if you move to the second SEVIRI instrument over the Indian Ocean with a slender angle, with the back scattering or forward scattering that you need to apply in the morning and the afternoon hours, only then you can start seeing these plumes, and you'll see that. So during daytime, not really. But as the sun goes to lower angles and you have the strong forward scattering, you start seeing this cloud. See, so unless the conditions are very good, you don't see it nowadays with SEVIRI, which is not the case with the cloud type RGB. It's quite apparent. Even true color RGB is not that powerful, as you see here. Also, I wanted to use one example from a local example, and this is where someone could help me, but I think we're around about here with Fort Collins or whatever. Yeah.
We may be further north.
Further north. Oh, yeah. Okay, it's Colorado. Very interesting event where you had everything in one event. You had the snowfall, you had the record temperatures in the north, maybe the next day, thunderstorms, tornadoes, fires, name it. What's interesting here is dust here, dust lifted with the strong wind events. And if we compare this, okay, another interesting thing here before I compare is this greenish signal, which means lack of red components. So this cloud is the tip of the cloud band is a little bit lower, but still icy. So you see how much information you can get from the clouds as well. But looking into this dust event here, so dust is conveniently as in dust RGB pinkish shades, but you see not all the dust is picked with this RGB, simply because 1.3 doesn't see low enough to cover. Okay, I'm just comparing to cloud type RGB where you can also see the wildfires that you cannot see with the 1.3 or sorry, with the cloud type RGB. But you see that this dust is higher and thicker. So I'll show an example of how to utilize that further on. Anyhow, height assignment of aerosols, actually the dust in this case, could be done by this RGB. So there's a potential there. High clouds, obviously, example over Europe in red, very thin, semi-transparent cirrus clouds. This is traditionally what we use to track down the thin cirrus. This is BTD difference 12 minus 10. It's one of the beams of dust RGB. And normally dust RGB is a good one to show these cirrus clouds like contrails around here. But still, this RGB is outperforming what we have today. And of course, if we go to solar cloud type RGB, cloud phase RGB or natural color RGB, you lose the signal completely. We're still at the cloud type RGB, and I'm showing this exactly the same example with the cloud phase RGB, the difference in snow colors here. We see the difference in snow colors as well, but not concerning the cloud, the ice particle size, but concerning the height. So the higher the snow is, it turns into yellow because the red component kicks in. Of course, if you have very dry air over, I have example, but I have no time to show. If you have very dry air advecting over the snowy scene, the snow turns into yellow as well, because the 1.3 can see deeper through the atmosphere and even to the ground. Lower grounds sometimes. So just an example, you see that the microphysical signal is not fetched, but the height assignment is. Yeah, that's another example of that. It's just a high cirrus, very funny looking contrails with shadows over the stratus in the south of Germany. You see it's picked up by this RGB, but not with natural color RGB or day microphysics. Dust RGB, as I said, did pick up this this signal of the original contrails, but there is no shadow, obviously, in the infrared, and with shadows we can see over stratus in the visible range. And maybe the last of the prominent candidates is obviously fire temperature RGB. Not much to say there. We are moving from seeing fires to seeing fire intensity. So this is, just to point out, this is one of the biggest fires that you can come across in Europe. In Europe, fires are normally smaller. So this is Algarve resort. A touristic region in Portugal received actually had huge fires in 2018, and you can see the fire intensity utilizing 3.9, 2.2, and 1.6. Then this fire spread southwards, and the front line of the fires is still visible, but with the small fires you don't catch this intensity. And the fires are at the lower intensity, talking about the fine tuning, so maybe some tuning should be done there. And just burn scars, burned area is seen in this example at the end in the brownish colors. Comparing this to SEVIRI, what we have today, we see the burned area in much worse. Yeah, so yeah, it's whoa. I want this, yeah. So this is, I want this in what we spectrally have today. So this is resolution of FCI over Sweden. Natural color RGB that we are utilizing today. We see the smoke. What we don't see a good way with the fire RGB, I forgot to say, is we don't see the smoke really. So with the getting towards the lower wavelengths, we start to seeing smoke in bluish here shades, and the fires are just reddish in this RGB. So we don't have the today in the today's suite of RGBs, we don't have the intensity information. Okay, aspirational products. So the work has been done, some work around this, and mostly we concentrate on to, as I said, 0.9 channel, which is absorbing channel in the solar range. And this is not an RGB. So as a teaser, I just put this one first. It's just a black and white single channel with some color shading here. And why I did that, because if you set the full range, just to make a point, if you set a full range for this channel, it can give you the low level moisture. We are over Germany here, and we have a dry line around across Germany. So behind the front, very dry front, we have a dry area ahead is very moist in dark blue, but still you have also information about the small cumulus fields, lower clouds, and very high reaching clouds in white. We'll come to that. Anyhow, I won't go into details of that. So what's happening with this channel? So as the signal photons are coming from the sound down, they get absorbed, they bounce back with some reflectivity, they lose intensity, they go back through the same atmosphere, and they lose intensity again. So it's just a simple absorption of photons, but depending on the wetness and dryness of the atmosphere, you get different response. So starting from this image, if we compare this with what we have today, the only tool for the low level moisture is the BTD difference 12 minus 10 blue component of dust RGB. So we're using still dust RGB to catch the low level moisture. It outperforms according to this proxy data. So this is another example from 2018, June, convection over Central Europe. So this is Austria, Czech Republic. And we see that this height information is contained. Why? Because the lower you go, there is more absorption and the less reflectivity from, say, equally reflecting clouds. If they're thick enough and reflecting the same, they are darker as lower as you go. So so this is full range of reflectivity here. And if I go to the lower end, if I just fetch the first, I don't know, 20% of reflectivity, these clouds don't get much information on the height, but I get better the information about the moisture fields. Okay. So this is what in essence this channel is about, and if we compare this to what we have today, we see this moisture boundary, but less prominent here with arrows. You can track these. Won't go into details. And what I had, one of the ideas is to combine actually in the one RGB one channel, but two different ranges. You see here, full range and the lower end, and 1.3 channel. You get something like natural color RGB, but with the moisture information. You have the information about the height of the clouds and the phase as a proxy. If we combine 1.6 channel here, you get more of the phase information. And if you play a little bit with the changing around the beams, you get the different appearance for the same thing. But when I change to this 1.3 being red, 0.9 blue, and 1.6 green, I got something similar to cloud type RGB, but cloud type RGB with the low level moisture information. So you have the phase information, you have the height assignment, you have the low clouds, high clouds, thin clouds, thick clouds, but on top of that, you get the moisture fields in the cloud-free area. Some ideas from Hans-Peter Rosli. He used as a well, I use the single channel, he used this difference between 0.9 and 0.8, the ratio, it kind of lifts up the low level moisture signal. And he had some ideas putting this in the, say, natural color RGB setup. Instead of green 0.8, he put this ratio, and this is the outcome. The similar thing for the dust RGB, giving this ratio to green beam, you still see the low level field, but I think the previous one had more on the clouds. And the last thing, oh, I did put the alarm, okay. And the last thing is some kind of low level moisture RGB where you utilize the BTD and the ratio between 9 and 8. Just an example of potentially new RGBs, and in essence, I try to play with what could be amended to fire RGB, because I've had a feeling that fire RGB doesn't provide a situational awareness, so the other clouds cannot be seen. I had an idea to change maybe 1.6 with 1.3 for the clouds. Also 24 hours, if you want to have a clouds 24 hours, you should be in the infrared only. So this is one example, and if you want to go in microphysics of the clouds, you add a couple of combinations, but I won't go into details of that. This is just example of these RGBs during daytime and during nighttime. You don't really lose the intensity information from fire temperature RGB to these other combinations, but this is just as aspirational ideas. And what's new with the oldies, that the RGBs that we were using in Europe for past 20 years almost, is suddenly we start seeing the microphysical or the temperature information on top of the clouds. If you look at the high thick clouds with SEVIRI, you just get red. And we noticed you start seeing some cloud top features with the newer advanced, maybe radiometric resolution, and this is just confirmation from the visible range that you really have something going on top of the clouds. This is AECP above anvil cirrus plume, first time detected above the anvils. Of course, for the better characteristics of the ABI, you start seeing the smaller differences in colors. So this is an example from Argentina, just confirmation from the visible. Also, what I've seen, start seeing in the low level moisture field with the dust RGB, and this is very faint here on the screen, are these low level moisture streets. Maybe you see them, just the lines of low level moisture, potentially areas of cumulus formation. This is just as a last example. As I said, 1.3 can be can amend information about the height assignment of the aerosols. So I combine it in the sandwich, the typical dust RGB and the 1.3 that gives you the height of the dust. So this is just looking, oh yeah, I have these examples I excluded later on. Anyhow, this is for the better signal to noise ratio, actually the NDT characteristics of ABI, you better see the low level stratus characteristics. There is much more shades that in a typical 24-hour microphysics of SEVIRI. This is just comparing resolutions during nighttime. For the fog, obviously with FCI, we are really looking into it. Okay, this is an example from Hama. So they were forecasting the fog in Senegal using SEVIRI data, and they obviously missed this patch of fog. When I looked at this with GOES, it really starts to be prominent. Later on, it was prominent even with SEVIRI, but at the dissipation stage, you just couldn't fetch these two patches of the fog. This is the volcano eruption changing the microphysical signal of the low-level clouds, seen by SEVIRI and seen by the GOES. So definitely a difference there. Natural color RGB over Adriatic. You couldn't tell what's happening there, but with the advanced resolution, you start seeing the island and the snow there. Just another example of that. This is a fog RGB, just utilizing high resolution visible channel. So in future, that will be 0.6 channel at 500 meters, looking at the small details of the cloud. And I think this is the last one. Convection RGB and the high resolution visible channel over. This is the stream over Pyrenees. You see the waves behind the Pyrenees and the high cirrus wave clouds, which are typically red because of their microphysical signal. It's small ice particles. And yeah, take questions with that.
Hi, Ivan. Thank you for your first impressive presentation. I just interested with the fire RGB that it could. How about the tropical region? Do you consider to develop especially for 20 hours RGBs for tropical region? What do you think? And because for El Nino event, we have more cases of smoke in the Borneo, and it impact many country around, like Singapore, Malaysia, Thailand. So it's very useful for us in tropical region if you consider for develop in June that in tropical receive. Thank you.
Excuse my ignorance, maybe. When I think of the tropics, I always start thinking where is the moisture and how well is damping the signal. In this case, you don't have moisture signal in any of these channels. So tropical tuning, to my understanding, it shouldn't take much. I would need to think maybe the size of fires you have there, the flavor of these, but it should be fairly similar to what we actually what the colleagues in US and Asia are using already with the fire RGB. This is just my ideas on amending the information, because fire RGB relies on the temperature signal from 3.9, which detects the say any temperature fires even lower, but then you start seeing signal at 2.2 depending on the plant function, and 1.6. So you kind of, if you combine all three, you get the intensity. For very hot fires, 1.6 start to see them. But if you start using this 1.6, the hottest fire signal, if you use this beam for something else, for cloud identification, like in this case, you kind of have the more of situational awareness. And even in this example, 24-hour RGB, you're not using any of solar bands, but only IR. So you're amending 3.9 with 10.8. And 12 minus 10 for the cloud information as well. You're having like a uniform 24-hour view on the fires. However, during this 24-hour RGB doesn't say so much about the intensity as you see here.
Thank you.
So I mean, we can take
this. We can discuss more. Yes, thank you. Thank you very much.
Thanks for your presentation, Jordan Girth with the Weather Service. This question is part serious and part humorous, but is there a risk of RGBs becoming too colorful for them to be useful? I mean, there's, in an earlier presentation, Carl showed an adoption of the snow fog RGB, day snow fog RGB to do blowing snow, which I almost saw as a separate RGB. Your RGBs are very colorful. Some of the examples have very many different applications for them. what's the best, is there a thought on what the best approach is? Do forecasters need, I think this was one of them I had in mind as well.
Yeah.
You know,
I thought so.
what are your thoughts on, should we have RGBs that are very good at one thing, like blowing snow or low level moisture or have you, or should we just go crazy with the colors and it's up on the screen, the forecasters can understand it that way?
Yeah, I think it depends on the who is using the product. If this is, I cannot find the example easily. Maybe ship routing company that is mostly interested in other things, but a little bit on the clouds. Then you want to maybe provide in one RGB the most situational awareness that you can. From my experience, the more color you can get from the RGB, the rich in information you are. Testing the new stuff here requires more colors, because this is what you want to accomplish. You want to have more colors when you're testing, and then you're kind of peeling off what is not necessary. So if you're thinking about nowcasting here, you want to keep all of that. Okay, because you're interested in the phase, you're interested in the height, thickness of the clouds, but also low level moisture. But if you would have a winter situation and you're looking into snow, so maybe you would kind of change the range for 0.9 to say more about the clouds, but not the moisture. So you would focus more. But I don't think there is a one answer to your question. I think it depends on the applications.
Javier has a follow-up.
So I've been working on this problem that Jordan mentioned. I'm working on detecting burned areas using the Dayland Cloudfire RGB, and there's a lot of noise that I don't want to see. I just want to see the burned area so the forecasters can see the flash flooding areas, potential flash flooding areas. So what I'm doing is I'm thresholding and trying to composite the information from the RGB into like a single like binary classification. I think one of the points of this workshop can be trying to isolate information, because yeah, that is like very noisy. It could be confusing. Forecasters may not use it for that reason.
Yep, and well, it depends. If you're more into development, again, you would like to focus on your thing you're doing. But I really appreciate, and I've seen wonderful examples from Dan on the pre-convective environment. Just this brightness temperature difference in colors is beautiful. You don't need anything else, and this is what forecaster needs prior to convective development. So sometimes it's really nice to have a one channel or channel difference. You put it in color and it does the job. But I know it's hard to get the products into the operational setup. I think on average, to my opinion, in Europe, average forecaster uses 3 to 5 RGBs. Maybe you want to kind of get them as much as possible in the lower number of RGBs. But well, yeah, I don't have strong opinion there.
So, excuse me. Thank you very much, Ivan, for your presentation. I have a few questions for you, because as you said, forecasters, they really want to concentrate on the products that from which they can fetch the useful information. So I have a question about the cloud phase and the cloud type RGBs, because in the tropics, particularly in the semi-arid areas, when we are monitoring convection, there is one feature that is very interesting. That's the gust front, because most of our the gust front.
Okay.
Yes, most of our systems are square line type, and forecasters really interested in seeing that gust front, which can give you them useful information about the convective system. So my question is simple: if you should recommend among the cloud phase RGB and the cloud type RGB, which one will you recommend to monitor the which one we would recommend to monitor the ghost front. And then regarding the low level moisture RGB, we used to follow low level moisture with the dust RGB, but there is always a possibility to, I mean, to how could I put it? To confuse at times low level moisture with other features. Is that could that be the case in the low level moisture RGB you are showing? That is there any risk that you may confuse the low level moisture with other features, other surface features? Because that may be a concern for practical use of these RGBs.
Yeah, that's a good question.
And then the last question, my last question is about the cloud phase RGB, because sometimes what we have noticed is that in some RGBs, the appearance in the mid and high latitudes of all these phenomena may be quite different from their appearance in the tropics. So I would like to know if you have investigated that aspect or you have not yet investigated it. Thank you very much. About cloud phase and the cloud type.
Okay.
The cloud phase and cloud type.
Okay.
Thank you.
So, yeah, I think that these are good questions. And the first question about the squall line and the outflow from the thunderstorms, I think it's good that we are at this slide. So you can imagine on the smaller scale, this being the outflow. So I think something like this would be very useful, because you see the push formation of the low level clouds in this pale yellow color, but you can also see the moist and the dry area. So I think something around this would be the perfect solution, because if you want to have a cloud type and a cloud phase, they will have similar information about the low level clouds, but you don't get the moisture information. So something that contains the cloud classification and the moisture information would be, I think, of a good use. Second question was about the, excuse me. Oh yeah. Yeah, with the dust RGB, that's correct. Dust RGB reacts also if you have some for instance, dust, which kind of gives you the opposite difference between 12 - 10, and also different emissivities of the ground can change the signal, so you can be confused. I know that with the low level moisture RGB having 0.9 channel, let's say we have this one and a few others, there is a vegetation information there, so this could mislead you in your, especially on the smaller scale. If you're looking at the outflows, moisture fields, this could be a reason to be misled by a different backgrounds. So caution there, definitely. And the last question, tropical use of cloud phase RGB, I think it's quite fine to use it as is, because there is no moisture information. With 1.3 with cloud type RGB, I didn't test enough. I wouldn't know what to say. I was looking at some tropical cyclones, and then we were mostly concentrating on the higher clouds, not really paying attention what is happening in the lower levels. But I'll get back to you if I find a good case to have a better idea on that. But good questions, thanks.
One last question before lunch.
Thank you, Ivan, for your brilliant presentation. My question is about the true RGB products.
True color.
the true color RGB products, will it be used during all the day or just the daytime?
Sorry, again?
The true color RGB.
No, yeah, it's just a daytime application.
So then which products you will use in the nighttime?
Yeah, well, it depends on the applications. From, let's say, we have applications from aerosols. There we would use definitely the dust RGB. What else? Yeah, we don't get the dust color. Smoke. Smoke during nighttime. I have a very good example of fires, and I think Dan was working on that one as well. In 2020 fires in California, I think the smoke was very much visible during nighttime using only infrared channels, or daytime, doesn't matter. Simply because the nature of smoke was different and the smoke particles were bigger. So if you look at the nighttime, unless you have a big smoke particles with the longer wavelengths you're using in the infrared, you lose the smoke signals. So across Europe, I haven't seen fire that was visible during nighttime. So yeah, tough luck, I guess, there. This is absolutely no-go, and ocean color, definitely. However, I have a good case on the ocean temperature. So just if you want to track features like ocean circulation through ocean color here, you could do that through temperature information. And there is a nice case we did with the Labrador Current, where very small differences in temperature were picked up by ABI, which was performing very well in that case. So this is nighttime signal of that. And I don't know about floods. I never tracked floods during nighttime.
I've had some experience with floods at night. Sorry.
Probably the water temperature.
Thanks. Yeah, I've had some experience looking for floodwaters at night using the nighttime microphysics, and that's mainly coming from the signal from the split window difference, the 12 minus the 10.3. There's a very stark difference between just normal land and any sort of like body of water, as well as the thermal difference, as you kind of mentioned. That kind of helps tease it out a little bit as well. But the floodwater has to be spatially large enough for the satellite, of course, to pick it up.
Okay, interesting.
I chose to not, for the sake of brevity, to not show it in my application, but I have used that. Yeah.
Okay. Thank you.